Okay, welcome back to our series on mechanical engineering thermodynamics. Today I'd like to briefly talk about some forms of work that we'll encounter when we're doing a first law energy analysis of control volumes. So starting off, we're going to talk about electrical work or electrical power. This is if you have like a resistive heating element with a given voltage and current passing through it inside of your control volume. So we've got three different equations that we can use to express electrical power. That's that W dot sub E. We can either use voltage times current, current squared times resistance, or voltage squared divided by resistance. All those are in watts, which is joules per second. And really, depending on what the problem gives us, depends on which equation we're going to use. Now, if we're doing an analysis that's not on a per time basis, that's just from one state to the other, we're going to use one of these bottom equations where it's just capital W sub E equals any of the top three times delta T is really what you're going to have. So voltage times current times delta T would give you joules of electrical work done in your given control volume. Now, in the rare case that you have non-constant voltage or current, you might have to use this integral definition of electrical work, which is just integral from state 1 to 2 of voltage times current times delta times dt. But for the most part, we'll be able to just use these three equations for electrical work or electrical power. Moving forward, we might have some shaft work in our control volume, and the equation that we're going to use there on a per second basis is W dot shaft equals 2 pi N dot times torque, where N dot is revolutions per second of your shaft. Or in kilojoules, we might have work done by the shaft equals 2 pi N times torque, where N there is just total number of revolutions. And this will be in units of kilowatts or kilojoules, depending on if your torque is in kilonewton meters. And then finally, we've got spring work. So this is if we are compressing a spring from one state to the other, one distance to the other. So that equation is going to be work of a spring equals 1/2 K, which is the spring constant, times x2 squared minus x1 squared in kilojoules. So these are just some common equations that we might have to use if we're doing the first law analysis. But most of the time, we're going to solve for work just using an analysis of energy inputs and outputs with the first law. So this is only in the case where we're given like some physical information corresponding to the quantity of work that's performed that we would use these equations. And one other thing to keep in mind is that we can also have what's called boundary work, where the boundary of our control volume is changing during a given process. And we're going to discuss that further when we talk about control volumes. So in the next video, we're going to do some examples of energy balances using these equations that we've learned so far. And then we're going to start talking about first law and how we use it to analyze energy flows through a system. Thanks for watching. As always, let me know if you have any questions and stick around for the next video.